So, we have seen how the individual waves are obtained from a random record using either the down cross method or the up cross method. So, from this kind of an analysis you will have T and Hi, and I said earlier that the recording should be in such a way that your number of waves should be at least 100. Okay. So, that means here I will be varying to 1 to n. So, having obtained the individual wave heights and periods, we can look at other characteristics like wavelength, etc. So, wavelength, as you know, you use the dispersion relationship as we have indicated here, and all of us know about this dispersion relationship, through which you can arrive at the wavelength of individual waves, and also since H is also known, Li is also known from the dispersion relationship, you can arrive at the wave steepness. And any other parameter also you can arrive at using this method of analysis. We usually describe the general wave characteristics in a random wave. The wave height is that usually we normally use the significant wave height for representing the characteristics of a random wave, and the frequency is referred to as peak period or zero crossing period. I will come to this later, but as far as statistical analysis is concerned, we normally use what is called as zero crossing period or average zero crossing period. This average zero crossing period is just you have the average zero up crosses, using the up crosses you have got the wave periods. So, mean of this can be just zero up crossing period, or similarly if you have the T high from the down crossing method, we call it the average of that is the average zero down crossing period. So, the same Ts, Tz is also straight away can be obtained as the duration of the record divided by the number of up crosses or number of down crosses, the meaning is same. We also use another period which is Tc, which is also called as, which is referred to as crest period, in which case the crest period is obtained as duration of the record divided by the number of wave crests. Epsilon is what is called as spectral width parameter, spectral width parameter. The spectral width parameter we usually have epsilon. This is given as 1 minus Tc divided by Tz to the whole square. So, this spectral width parameter, what kind of information it gives? When we have a combination of a number of waves with different wave heights and wave periods, then you will see that you know that the wave period can be represented as frequency, which is 1 by T, that is the frequency, and you know that Hi is nothing but energy. Okay. Now, if you want to represent a random wave, the characteristics of a random wave, which is comprising of a number of composites, number of sinusoidal components with different waves and wave periods. Then how do you represent this? One way of representing is frequency on the x axis I can get, and on the y axis you will be drawing half into amplitude square. Amplitude is nothing but hi by 2. So this curve gives you some information about the distribution of energy. Now whether this curve is a broad band or a narrow band. What do you mean by broad band? Broad band is something like this, wherein you see that the energy is spread over a wide range of frequency. Narrow band is something like this, where the energy is spread over a very narrow range of frequencies. So this can be determined from the analysis of ocean waves, whether it is a broad band or a narrow band. You are expecting, you can expect either a broad band or a narrow band, which can be determined by the value of the spectral width parameter, and that spectral width parameter in the case of the statistical analysis can be obtained as epsilon equal to square root of the ratio of Tc and Tz whole square. Is that clear? Okay. Now all the other efforts were towards representation of a random wave in terms of a single parameter which can replace the effect of the entire random wave. Some way of representing, some statistical measure to represent the random wave. It was the first, one of the earliest paper was by Tucker. The method of analysis is very simple, very straightforward, and is quite handy in arriving at the value of root mean square value. So we normally come across h1/3, h bar, hrms, h110, h max. These are the different statistical measure of the wave heights, which are usually used in the wave mechanics or for the design of structures, etc. So in this case you see this root mean square value can be given by that long formula, wherein you see that h1 is the distance between the highest crest and the lowest trough. So highest crest is, this is highest crest from a sample record I am just showing, and the distance between that and the lowest crest, so lowest trough, I will just say that this is ending here. So the lowest trough will be obviously this, I just make this something like this. So obviously this will be the lowest trough. So this is your h1, and the second lowest crest is this, and second lowest trough is this. So obviously the distance between these two is your h2. So this will be your h2. So then theta is log where nz is the number of 0 up crosses. Using this simple formulation you can arrive at your H RMS, and once your H RMS is obtained, then your H max is given by this formula, the one just above the maximum wave characteristics and other parameters are given as we have 3 different formulas there. The first one is H max, which is of course going to be a function of HRMS and theta, okay, and HS is equal to 4 times HRMS, and the final one is H110 is 5.09 times HRMS. Thus you see that you can arrive at the values for the different parameters that are in use. That to some extent we have covered the different statistical methods, different parameters under statistical method. So under the statistical method analysis you have H1/3, which is nothing but the average of highest 1/3 of the waves. So if you have 100 waves, you arrange them in descending order, take the top 33 waves and take the average of that, and that is going to be your HS, significant wave height. The significant wave height is usually used for the design of breakwaters, because as I said earlier, breakwaters are kind of flexible structures wherein the kind of failure you can anticipate is rolling down of the stones, so that the waves give us enough amount of time to rehabilitate. So it is enough you design the structure for significant wave height, and usually the H max is avoided for the flexible type of structures. I am flexible in the sense I am talking about rubble mount breakwaters. The other parameters are your HRMS, which is nothing but the root mean square value, then H110, similar to H1/3 we have H110. H110 is widely used in the field of naval architecture also, and then finally you have the H max, which I did not have to mention what it is. But you see that there is a kind of relationship between the different forms of representation of the wave height. So we have to some extent understood the statistical analysis of ocean waves, or a representation of the average wave characteristics in the statistical domain. Now let us move to spectral method. As we have seen in the classification, under spectral method you have 2 different methods, which is one is via the autocorrelation function, the other one is via FFT. So these days you have what is called as WAFO under MATLAB, which gives you the distribution of energy in the frequency domain referred to as spectral density, and the shape of the curve as shown earlier, that is, this will be, that is nothing but half into amplitude square. Usually it will be something like this. So you will have a something like this. So when we have an analysis or random waves, the usual way is subjected to spectral analysis or frequency domain analysis. The main purpose for this is to get the spectral density curve. That is how the energy is distributed and as a function of frequency. Before this WAFO under MATLAB, we have to do it on our own, write a small code and then try to get all the informations about the distribution of energy, etc. So under the spectral and under the autocorrelation function, in order to perform the spectral analysis, this record is assumed to have a number of lags. We usually take the number of lags or the components as 10% of n. N is the number of data values. What do you mean by number of data values? Number of digital values. So this will be either positive or negative. Okay, you digitize the random record at regular intervals, constant sampling interval, and then take 10% of the total number of data as the number of components. Once you are done with that, you can estimate what is called as autocorrelation function. The autocorrelation function is given as 1 minus 1 divided by n minus r. R is the lag number and the number of lags will be maximum of m, which is 10% of the number of data. So if the number of data is 1000, you are supposed to have 100 frequency components. So this autocorrelation function, if you have a time history, it correlates within itself. As you see, it is correlating within itself, that is I into x of I plus r. So you have a I value here and then you multiply that with a lag and then you get the autocorrelation function. So when RR is given by this, what will happen if R is 0? If R is 0, it is nothing but the mean square value, okay, that is root mean square value. If R0 is put in that expression R suffix R becomes 0, so that is naturally your mean square value. So this is nothing but root mean square value, okay. Is that clear? So now you see that the smooth spectral density estimates are estimated for the different lags by using this expression, where DRR is given by this expression, where R is ranging from 0 to m, D equal to 0 if R is equal to greater than m. That is the assumption. So all these parameters are known to you, so you can arrive at the variation of the spectral density curve. So further details you can refer to a number of books available on this aspect. If you draw RR divided by R0, this is what is called as autocorrelation coefficient. What does autocorrelation coefficient indicate is, autocorrelation coefficient indicates that if you subject or determine the autocorrelation coefficient for a sine curve, maybe you get the variation like this, okay, the same curve will be repeating. If you are having a random time history, then autocorrelation coefficient will be varying from, maximum will be 1 at 0th lag, okay, because look at this expression. So it will be varying like this, okay. If the autocorrelation coefficient dies down very quickly, then we say that this is really a random phenomena, a random wave. Sometimes what would happen is that this would not die down, but it would be oscillating something like this. That means although the time history is looking more or less random, but it is not that random, but there is, because of certain dominant period which is really built in the random waves. So this is because of the existence of a particular periodicity. Is that clear? So such informations you can arrive at autocorrelation coefficient. The other aspects which I am not going to cover, but you need to be aware of that, are the cross correlation and the, mostly the cross correlation. Cross correlation will be, you want to correlate two variables, one is maybe wave and force. You have to, how well is it correlated between these two variables. So all those informations can be obtained. So I would suggest the book by Bendit and Pearsall, which is given in the at the end of the reference, for further details on cross correlation, autocorrelation, and even all these methods which I have discussed. So when you write a program, for example you want to write a program on your own to check whether the spectral density estimates are going to be correct, then you have the spectral density curve using the formulation. You just find out the area under this curve, that will be m0, which is referred to as 0th spectral moment. You have to find out the area, and after you have a signal, you use your sum method, you get this. After getting this, get the area under the spectral density curve, and that is going to be your m0. Earlier I said r0, that can also be calculated as I have said earlier. And for the time history, for this time history, straight away you can get your standard deviation, which is sigma eta, okay. So now m naught will be equal to this is the kind of a cross you can just use this as a basis for checking your results. As we have seen earlier, what was done in the statistical domain, we did the what we normally do is we observe the probability density function and then we draw whether it follows a standard distribution. For the wave heights, I mentioned a few like your Rayleigh, Weibull, etc. We saw all these distributions, and I also explained the importance of comparing the probability density of measured wave heights with a particular theoretical distribution, because once you have done that and once you see that it follows a standard distribution, then it becomes very handy for you to arrive at a lot of information about the process. Likewise, like you have in the probabilistic approach, in the spectral approach you have several standard spectra, and the idea would be to draw maybe this dotted lines may be your measured spectra, and then you can compare with other standard spectra. Maybe this is following this, or maybe there is another spectra. So you can verify or find out which of the standard spectra it could follow. But what are the standard spectra? Similar to the standard distributions, we shall see about the standard spectra later after having some basic information about the spectral method, and we will also try to understand the methods using some worked out examples. So once you have drawn the spectral density curve, once you have the spectral density curve, so f and s theta of f, you have this, okay. Then I know at each of the frequencies what is the value of s theta of f. So I simply use that expression m suffix n, where n is the order of spectral moment. So this will be spectral density multiplied by frequency to the power n. N is the order of spectral moment. Usually we have n equal to 1, 2, 3, 4. Of this we use all the spectral method spectral moments, but the most widely used spectral moment is the m naught. That zeroth spectral moment is nothing but the area under the spectral density curve, which I had already explained. So once you have got this, and once this is obtained, then you can easily get the values of the different parameters, like your spectral width parameter. Spectral width parameter, you remember under the statistical method you saw it is a function of crest period, average crest period and the average zero crossing period. So that was under the statistical method. Now this is under the spectral method. Under the spectral method you see you can arrive the spectral parameter h bar, that is the mean wave height, then you have the hs significant wave height, then you have the h110, h100 and the tc average crest period and the average zero crossing period or average period for that matter. So that will be square root of m0 by m2 and m4 will also be coming. So mostly it will be only m0, m2 and m4. So now you have a good exposure on, I believe you have a good exposure now to the method of analysis of motion waves. And what do you do? Why do you do the analysis? So we have seen statistical method and the spectral method. Under the spectral method, here we had the up cross and the down cross, which we have already seen. Now under the spectral, we have the spectral method via autocorrelation, and now much faster and easier method, that is the fast Fourier transformation. Unlike the selection of the number of lags in the spectral method via autocorrelation, here the number of frequency components will be n divided by 2, that is the number of data values divided by 2. So if you have 1024 data values, then you will have 512 frequency components. This is more accurate, more simple and straightforward, and you need not have to sit and write programs for this. Only thing is you should understand what the fast Fourier transformation gives. Again for a detailed description you should refer to the book by Bendit and Pearsall, which gives the complete analysis of this kind of random signals. So here it says that estimation of the spectrum from a finite sample and to state how closely this estimate can be expected to be approximately true spectrum. This is achieved by FFT. This is nothing but the basic Fourier series. So any random signal is assumed to be formed by a number of Fourier series components, okay, and that is why the eta of I is represented as a number of components wherein an and bn will be there, and the one inside cos and sine will be the phase. Eta of I is the water surface elevation, and that will be having a zero mean process, that is a zero mean process. What do you mean by zero mean process? You have the time history, you take the average, and once you have taken the average, subtract it from the actual time history. So that will be your mean zero process. So the elementary sample estimate of the spectrum can be defined as the spectral density is given as here. So you estimate the frequency components, that is A1 consisting of An and Bn, and then this once you arrive at these values, the spectral density can be estimated. So I suggest, because I do not want to go into the details of the mathematical aspects of all these things, only thing is I suggest that you read some book. But what it gives, what it conveys, etc., we will have a discussion in the class. Of course this can be removed. So that is as far as the spectrum is concerned. Now we will get back to the statistical method, and we will understand more about statistical analysis as well as the spectral analysis of the ocean waves. So, initially here the fundamental premises of the spectral approach is that the random waves are the results of superposition of a number of sinusoidal components or simple sine waves that have a continuous frequency distribution. The process can be approximated with a finite number of small amplitude sinusoidal waves having discrete frequencies. So, what is the total? Suppose if you have n number of wave components, what is your energy? Energy is what? Energy is gamma by 8 into h square. So, here I have h number, so I can write this as okay, and each of which will be having associated with a frequency. So, let us consider this problem. Find the energy distribution of an irregular seaway composed of 6 different components. So, when you are dealing with ocean waves, actual ocean waves, you will be dealing at least with 100 components. That is what I have said earlier. The 6 number of components very less, just to make you comfortable with in understanding the problem or the picture, why you need to go in for what exactly is the spectrum, etc. That is the reason I have taken only 6 different components. So, for each of which I have given you the wavelength, and of course I will to make it simpler I consider only deep water conditions. Wave heights are given in the bottom and wave lengths are given in the second row. Now, you know that this is equal to GL by 2 pi is your celerity. Hence, I can arrive at your sigma or so from this what is Wi W1 Wi is equal to 2 into 9.81 divided by 684, for example, for the first equation, first frequency component. Is that clear? Of course, there is a pi here. So, using the relationship between sigma, pi and c, you can arrive at omega 1. Is that correct? Okay. Is it clear? So, similarly, I carry out for omega 2, omega 3, omega 4 up to omega 6. So, I am having now omega I, which is nothing but 2 pi by 2 pi f. Okay. What I need is the distribution of energy. So, omega 1 is 0.3, 0.3 for 0.3, that is the wave number 1. I calculate what is the amplitude of amplitude square. So, you see that here the gamma is there and 1.5 is the amplitude, 3.5 is the wave height, and similarly 3.5 here, this is 1.75. So I add up all these values and what do I get? I get the total energy as equal to 94582 Newton per meter. What does that mean? That is the total energy contained in these 6 waves. How can I draw that? I can represent as shown here. That is, this is omega 1, omega 2, omega 3 up to omega 6. But note that the distribution of this curve is given below, but in this curve, in this figure what we have done is the ordinates are obtained by dividing the individual unit, individual energy by the bandwidth. That is, for example, the first one, gamma into gamma divided by 2 into 1.5 square. This is the energy of the first component, okay, and that first component is divided by, each of the components is divided by the class interval. Class interval here is 0.3. Why do we do that? Because the area under the curve should be equal to the energy, total energy, that in order to make sure that the total the total energy is nothing but the area under the spectral density curve, and that is why we have divided the individual energy component by the bandwidth and we have obtained the ordinates. Is there any doubts for any of you? Is it clear? Okay. Now we have thus seen in the problem that the energy in the waves and that the area under the curve gives you the same quantity. Again please recollect, we are calculating the individual energy content for a particular frequency component, and that energy component we are dividing it by the class interval or the frequency interval, and that will be represented in the ordinate, so that the area under this curve gives you the total energy. Now instead of drawing like this, we know that we can simply, because that gamma is going to be a constant, right. So we remove this and we represent only half into amplitude square. So half into amplitude square. So when I can represent this, so this gamma g, so I mean rho g is divided throughout, and the area under this curve of the new curve now generally denotes as m naught, that is area under the spectral density is nothing but the m naught. We have removed that constant, that rho into g. Once you have calculated the distribution of the ordinates are here, and this is called as the spectral density of the wave energy. Very often we hear this spectral density, so this is what it means, and now you know the spectral density and area under that curve you simply multiply it by the, so I just calculated the area under the curve and that will be so much, and then you just have to multiply it by the gamma rho into g in order to get the total energy under the curve. Is that clear? So the useful information from the spectral density curve is the range of wave frequencies. What is the range of wave frequencies that are important to the contribution of the C wave, or in that particular area what is the frequency components? What do you mean by frequency components? See, for example, if an area has a curve like this and a spectral density like this, or it shows like this, you see the difference. So, for example, if you go and stand in this, if you have a vessel or whatever floating structure, for this frequency only you will see that it is exerting a lot of energy, so it will have more oscillations. For other frequency components, when I say other frequency components, when the wave period is reciprocal of this frequency, for those wave periods the oscillations will be less. And for example, the other aspect, so this will be a low frequency component. The low frequency component is more dominant here. So this will give you the range of frequency components which are very important for you to design, or if you want to evaluate the response of a floating structure, what is more important for is the frequency range. So the frequency at which the maximum energy is obtained. So this is what will be the maximum energy that would occur, the frequency at which the maximum energy will occur. The content of energy, so each frequency band I can get what is the energy content, and also the existence of swell at low frequencies. If you have a low frequency component like this, it is nothing but existence of a swell. What is a swell? Swell is which is outside the fetch.